Bayes' theorem can get a little more complex. Let's take a look at a small example, and what we'll do here is we'll mess a bit with the prior probability. So again, we have Alex and Brenda in the office, and we saw someone pass by quickly, and we don't know who the person is. So let's say we look more carefully at their schedules and we realize that Alex actually works from the office most of the time. He comes by 3 days a week. And Brenda travels a lot for work, so she actually comes to the office only 1 day a week. So initially, without knowing anything about the red sweater, all we know is that it's 3 times more likely to see Alex than to see Brenda. Therefore, our prior probabilities are 0.75 for Alex and 0.25 for Brenda. And let's say that we have this happening throughout all the weeks. But now we use our extra knowledge, which is that the person we saw had a red sweater. The rule is still as before, as Alex wears red twice a week and Brenda wears red 3 times a week. So naively, we would think that the real probabilities are not exactly 0.75 or 0.25, because Brenda wears the red sweater more than Alex, so they should be a little closer to each other. Let's calculate them. So we'll do the following. Let's think of the columns as weeks instead. So now, for each 5-day work week, Alex wears red twice and Brenda 3 times. So we color the days they were red. Now, since we know the person wore red, we forget about the times that they didn't. So we have 9 times someone wore red. 6 of them are Alex, and 3 of them are Brenda. Therefore, among 9 times we saw someone wearing red, 2/3 of the times it was Alex, and 1/3 of the time it was Brenda. Thus, our posterior probabilities are 2/3, or 0.67 for Alex, and 1/3, or 0.33 for Brenda. So it looks like we did a little bit of magic. Let's do this again in a more mathematical way. We saw a person, and initially all we know is that it's Alex with a 75% probability and Brenda with a 25% probability, since Alex comes to the office 3 times a week and Brenda once a week. But now new information comes to light, which is that the person is wearing a red sweater, and the data says that Alex wears red 2 times a week. So now we look at Alex. What is the probability that he's wearing red? Since a work week has 5 days, then the probability of him wearing red is 2/5, or 0.4. And the probability of him not wearing red is the complement, so 0.6. Same thing with Brenda. Since she wears red 3 times a week, then the probability of her wearing red today is 0.6, and the probability of her not wearing red is 0.4. Now, by the formula of conditional probability, the probability that these two will happen is the product of the two probabilities, P of Alex times P of red given Alex. Therefore, the probability that the person we saw is Alex and that they're wearing red is precisely 0.75 times 0.4. We multiply them and put the result here. We calculate the other probabilities in the same way. The probability that the person we saw is Alex and that he's not wearing red is 0.75 times 0.6. The probability that the person we saw is Brenda that she's wearing red is again the product of these probabilities, which is 0.25 times 0.6. And finally, the probability that the person we saw is Brenda and that she's not wearing red is 0.25 times 0.4. And now here's where the Bayesian magic happens. Are you ready? We have 4 possible scenarios, and you can check that these 4 probabilities add to 1. But we know one thing, that the person we saw was wearing red. Therefore, out of these 4 scenarios, only 2 are plausible. The 2 when the person is wearing red. So we forget about the other 2. Now, since our new universe consists of only these 2 scenarios, then the probabilities should be higher, but the ratio should still be the same with respect to each other. This means we need to normalize them, or equivalently, divide them by something so that they now add to 1. The thing we should divide them by is the sum of the 2. So our new probability of the person being Alex is the top one, namely 0.75 times 0.4, divided by the sum of the 2, namely 0.75 times 0.4 plus 0.25 times 0.6. This is precisely 2/3, or 0.67. And now we can see that the complement is the probability that the person is Brenda, which is 1/3, or 0.33. If we take Brenda's probability and divide it by the sum of both probabilities, we can see that we get 1/3 as desired. And that's it. That is Bayes' theorem at its full potential.